In this lecture, we are going to discuss the basic fundamental statistical concepts that are essential to interpreting and informing statistical analysis. Understanding of these concepts is essential for determining the appropriate statistical strategy when developing or analyzing research or evidence-based practice. Following this lecture, students should be prepared to differentiate between populations and samples and the associated data collection methods, compare and contrast descriptive and inferential statistics, explain key concepts related to variables, describe the 4 levels of measurement, and discuss the relationship between validity and reliability. As we head into this lecture, keep the information from the previous lectures in the back of your mind. Remember that statistics is a practical method for collecting, organizing, summarizing, and presenting our data. And as advanced practice nurses, we need to be able to apply statistics to make inferences about the population from which the data is collected so that we can generalize our findings and be able to apply them appropriately in clinical practice. Let's begin with some terminology of basic sampling concepts. The population, which you may see referred to as the target population, refers to the entire group of individuals that a researcher wants to study. There are a few instances, usually not in healthcare, where researchers are able to study all members of a population and collect data on all members of a population. When this occurs, the data that is collected is referred to as parameters. However, in healthcare, the ability to collect population data is nearly impossible. Therefore, we must rely on collecting data from samples. And a sample is a subset of the individuals from the population that the researcher uses data on to draw conclusions about the population. And therefore, when we are using data on a sample to make conclusions about a population, it is very important, as we will discuss later in this lecture, that the sample is well representative of the population. The numerical data that we collect on a sample is referred to as statistics. And in this course, we're going to discuss the 2 different types of statistics: descriptive statistics and inferential statistics. Just as the terminology states, descriptive statistics describe or depict the data. Descriptive statistics include measures of central tendency and variability. These allow data to be organized, summarized, and described in ways that are easily understood. Descriptive statistics may be described numerically as means, medians, and modes, or they may be described graphically in charts and tables. Inferential statistics use hypothesis testing to generalize the results from a sample to a population. This type of statistics is what researchers use to guide treatment decision, and this is the statistics that nurses use to guide practice change. Therefore, it is very important that the sample is representative of the population when you are using inferential statistics as your rationale behind practice change. You may have noticed that I've mentioned the word sampling a few times already. Why do we need samples? Why can't we collect data from the entire population? It's a very simple answer. In many cases, the population is too large to collect data on all the members, and it is too costly to be able to access a population as a whole. And in a lot of cases, we may not actually have access to every member of the population. Think about if you wanted to do a sampling of every person in the United States, or even simplify it to every person in Cumberland County, Pennsylvania. it would be very hard to access every individual. Therefore, instead of attempting to access every individual, which is a futile cause, we take a sample of the population and try to infer, using inferential statistics, from the sample to the population. And because of the fact that we are inferring, we need to make sure that our sample is representative of our population. Because in evidence-based practice, we need to be considering how the outcomes from the sample might relate to the outcomes for the population. And so when we are sampling, we're using samples to reduce cost. We want to use representative samples to improve our quality and enhance our generalizability. So let's look at some of our options for sampling techniques. There are two types of sampling procedures, random sampling and non-random sampling. We will discuss random sampling now, followed by a brief discussion of non-random sampling. Random sampling is a method of selecting subjects for participation based on chance alone. Random sampling is the stronger of the two sampling procedures. All types of random sampling select subjects for a sample based on an equal chance of selection for each subject. A simple random sample is a sample taken so that all subjects in the population have an equal chance of being selected. Usually, technology such as a number table or random number generator is useful in selecting the chosen number of individuals for the sample. Systemic random sampling begins by assigning a number to each subject in the population and then selecting every X person, where X is the population size divided by the desired sample size. In other words, if you have a population of 100 people and you want a sample of 20 people, 100 divided by 20 is 5. You will select every fifth person from the list. Systemic random sampling is straightforward and does not require the technology of a random number generator or number table, and is simple to perform as long as the order of the subjects is listed randomly. If the researcher is not careful about the order of the subjects, a non-random sample could be accidentally created. Stratified random samples are useful when a researcher wants to ensure that certain groups are equally represented in a sample. Samples are often stratified or split into smaller groups based on important factors such as gender, race, ethnicity, or income. And then random subjects from each group or stratum are selected. A stratified random sample is proportionate if the subject size of each stratum in the sample is proportionate to that of the population. For example, if I wanted to do a stratified random sample of undergraduate nursing students and I split the students into strata of male and female, I know that nursing schools are primarily 90% male, 10% female. Therefore, my sample should represent 90% female, 10% male. The accuracy of sampling when you use stratified random sampling is improved when the subjects in each of your strata are homogeneous. The subjects are very similar to each other, aside from the specific characteristic that you are pulling out to put them into different strata. So in other words, in our nursing school example, we would want all senior level students or all students taking a statistics class. We would want to have as many other characteristics besides gender to be the same to get the most representative and accurate sample. Finally, cluster sampling is similar to stratified sampling and is particularly useful when a population is large or when a study covers a large geographical area. A cluster sample begins by dividing the population into different groups, usually based on geographical area, called clusters. And then a certain number of individuals are selected from each cluster. Cluster samples work better when the clusters are heterozygous. In other words, when the subjects in the clusters are different from each other. As a side note, cluster sampling tends to provide less precise sampling than simple random sampling or stratified sampling, but cluster sampling is often a cost-effective and feasible approach to sampling that you will see done in practice. You will often see literature say that this number of nurses were surveyed from this region of the United States and this many from this region, or this many from research hospitals and this many from community hospitals. Those are all examples of cluster sampling. Random sampling procedures were reliant and dependent on chance. Non-random sampling procedures, in contrast, do not rely on chance, and thus members of the population do not have an equal chance of selection. Non-random sampling procedures prioritize feasibility or access to the population of interest. Therefore, the competent investigator must take care to collect data on all or the relevant characteristics of each participant, so that the representativeness of the sample can be ascertained at the end of the study. When using non-random sampling approaches, the researcher trades generalizability of the findings for feasibility of developing a sample. Use of convenience sampling is based on the accessibility of subjects in a population, and non-random convenience sampling is used extensively in clinical research. Nurses often do studies on the patients that are available and accessible to them. While this sampling approach saves time and effort more than any other method that we have discussed, it is less likely to be representative of the entire population. Consider if I were to do a study on graduate nursing students taking a statistics course, and I only use students in this specific course at Messiah University. My sample is likely not representative of the population of all graduate level nursing students taking statistics courses in the United States. Purposive sampling is a non-probability sampling technique where researchers intentionally select participants based on specific characteristics or criteria relevant to the research question. This method focuses on gathering in-depth information from individuals who can best illuminate the research topic rather than aiming for a broad representative sample. You often see purposive sampling done when researchers are looking for participants who have a specific disease pattern or a specific trajectory of disease. While purposive sampling can provide very beneficial information, researchers must be careful that their selection process does not induce bias, and researchers must be aware that replication of the study with such a specific sample can be compromised. Quotient sampling is done by dividing the population into mutually exclusive groups or groups that do not overlap and selecting individuals from each group, very similar to a stratified random sample. However, in quotient sampling, subjects in each group are not selected randomly. Rather, a researcher may take a sample within each group using convenient sampling. For example, maybe a researcher wants to study college students at Messiah University. And so the researcher goes into different courses where no two students are in the same course, and they take a convenient sample of the students present in that course at that time. Quotient sampling is limited in its generalizability because of the convenience element of the style. Finally, snowball sampling. Snowball sampling uses word of mouth or referral to accrue subjects. The researcher makes a primary contact with a participant who then notifies the researcher of other potential participants. Thus, the sample grows in a way similar to a snowball rolling down a hill. This method is particularly useful for finding hard to find or hidden subjects. Often this method will be used when trying to reach populations such as those who are undocumented, those who are involved with illicit drug use, or people that would normally not promote whatever the characteristic is that is being studied. However, like all non-random samples, this method of sampling is prone to producing non-representative samples of the population. Before we proceed, I want to pause to make a brief word about non-random sampling. Non-random sampling procedures are generally easier and more cost-effective to implement than random sampling procedures. Non-random sampling procedures are most likely the procedures that you will read about in the literature and the procedures that you will use when conducting evidence-based practice projects. However, you must keep in mind that there is a greater chance that non-random sampling procedures will not produce the most representative sample. When a sample is not randomly selected, it is less likely to represent the population than a sample that is randomly selected. And when a sample is not randomly selected, potential selection bias can be introduced into and affect the results. We are now going to move on to talking about variables. A variable is a trait or characteristic that changes or varies. And data are the values of variables when they vary. A collection of data values is known as a data set. To explain this in a very simple form, maybe researchers are collecting information on the age of nurses. The variable is age. Age changes from person to person. Therefore, the individual age of each nurse is the data collected, and compiling all of these ages together makes a data set. Investigators will classify variables according to a variety of different characteristics that suggest how these variables may be used in research and evidence-based practice. Variables can be considered either quantitative or qualitative. Quantitative variables are variables that are numeric, things like your age, your weight, your height. Qualitative variables are non-numeric, things such as eye color and hair color. For the purposes of statistical discussion, we are going to focus on the quantitative or numerical variables because these are the variables that are amenable to statistical analysis. Numerical variables can be either discrete or continuous. Discrete variables have values that are countable, but do not include fractions. In contrast, continuous variables have every possible value on a continuum. As shown in the picture, An example of a discrete variable would be 3 children. You cannot have a fraction of a child. Height, however, would be a continuous variable because we could measure height to the 10th, 100th, 1000th, or even smaller and smaller fractions of a centimeter. Variables can also be characterized as independent or dependent. Investigators look at independent versus dependent variables when they are investigating the interaction between two variables for statistical analysis. The independent variable is the variable that the researcher can control, or that the researcher is increasing or decreasing. The dependent variable, which I remember as the fact that a change in the dependent variable depends on what the researcher does to the independent variable. So the dependent variable is the variable that responds to or is affected by the independent variable. It's very important for investigators to clearly define what the independent and dependent variables are, because this relationship between what the researchers are predicting impacts something else is going to be crucial when the researcher decides what statistical methods are appropriate for data analysis. Once the researchers have defined the variables of interest, the next step is to think about how to measure these variables. There are 4 levels of measurement: nominal, ordinal, interval, and ratio. It is important to understand the levels of measurement because different statistical procedures will require different levels of measurement. These levels of measurement can further be broken down into categorical and continuous. Categorical variables represent groups or categories, while continuous variables represent measurable quantities. We're going to look at each level of measurement individually. In the nominal level of measurement, data are classified into mutually exclusive categories, as in each data point fits into one and only one category. The word nominal means to name or categorize. The key feature of nominal level measurement is that there is no ranking or ordering of the categories. We cannot say that one category is superior, inferior, more or less than the other categories. A common example of the nominal level of measurement is classifying people as male or female. In the ordinal level of measurement, this is also a categorical level. Data are classified into mutually exclusive categories. In ordinal measurement, we not only have distinctive categories like we had with the nominal level, however, we also have a clear ranking and ordering among the categories. One of the most common types of ordinal ranking that you will see is small, medium, and large. We are able to recognize a difference. However, the difference is categories, not necessarily being able to classify it as numerical, where we can say there is a set distance or difference between the categories. Moving on to continuous levels of measurement, which represent measurable quantities, we begin with the interval level of measurement. Data at the interval level of measurement are classified based on ranking and mutually exclusive measurement and specific distances between these categories. The distances between the categories in interval level data are assumed to be equal and are measurable. So we can't measure the difference between small, medium, and large, but we can measure the difference for the interval level. The key feature of the interval level of measurement is that there is no absolute value of 0, and there is no concept of ratio or equal proportion in the interval level of measurement. One of the most common examples of interval level of measurement is temperature. We can say that there are 35 degrees difference between 35 degrees Fahrenheit and 70 degrees Fahrenheit, but we cannot say that 70 degrees Fahrenheit is twice as warm as 35 degrees Fahrenheit. Finally, the last level of measurement is ratio, which is also a continuous level of measurement. The ratio level of measurement maintains all of the characteristics of the continuous level of measurement, but also includes a meaningful 0 and ratio or equal proportions that are present. The most common examples that we tend to see for ratio levels are weight and height. And if we think about that with the ratio level of measurement, if we have a person who is 50 pounds and we put them on a scale, and we have another person who is 50 pounds and we put them on that scale, we're going to get 100 pounds. If we put a 100-pound person on a different scale, it's going to equal the same 100 pounds. Level of measurement is very important because when we understand the level of measurement and we understand along with that the choice of statistical tests, this becomes our foundation for analyzing the literature. While determining the level of measurement of the variables is extremely important, another important aspect of research and evidence-based practice is choosing the best measurement tool. A tool, which is often referred to as an instrument, is a device for measuring variables. And researchers are tasked with making sure that the tool they choose will be the best approach for measuring their variables of interest. Strong tools reduce the likelihood of a measurement error. A measurement error is the difference between the measured value and the true value. Measurement error is unavoidable in research. However, it can be minimized through taking measures and steps using the concepts of reliability and validity. Reliability tells us whether or not a test or a tool can consistently measure a variable. Validity tells us whether the tool measures what it is supposed to be measuring. So if you look at the table on the left, ideally we want our tools to be reliable and valid. Reliable means that you are getting similar answers every time you use the tool. Notice how if we go down the reliable column, that the dots are all very close together, but we go down the unreliable column, they're far apart. Reliable is that you're getting the same thing over and over again. Valid is that you are getting what you want to get. If we look at the bottom left, we see the tool is not only reliable, the dots are all very close to each other, but it is valid. The dots are in the middle of the bullet. And so we're looking at how close are these dots to where we want them to be. Are they measuring what we want them to measure? We are now going to briefly touch on the three main types of reliability and validity. The first type of reliability is test-retest reliability. This type of reliability looks at, does the tool perform similarly over time? If a subject were to use the tool and then retake the tool without any other changes in learning or environment, we would expect them to receive a similar score on the tool. Inter-rater reliability is used to determine the degree of agreement between individual scores on the rating. This looks at how consistently is the tool being used. If I use the tool and use it to rate something that I'm observing, and you use the tool to rate something that you are observing, are we getting the same rating from the tool? And finally, internal consistency reliability. And this is one that you often see reported in the literature. And it is used to measure whether the items in a tool measure the same thing. Are all the items consistent with each other? Internal consistency reliability is usually reported as a Cronbach's alpha. Cronbach's alpha has a range from 0 to 1, and the higher the Cronbach's alpha, the more consistent the items are. We usually like to see the Cronbach's alpha above 0.7. There are also three main types of validity. Content validity is looking at if the tool is measuring all of the aspects of a concept. So if we have a tool that is about depression, we want to make sure that the tool is not only measuring changes in serotonin levels, and the tool is not only measuring changes in mood, but also measuring somatic symptoms. Criterion validity looks at how well a tool is related to a standard or benchmark. So what we look at, especially with new tools, is if we give somebody the new tool and we give somebody a tool that we already know from prior experience and extensive research is been determined valid and reliable, are the results on the two tools going to be similar? And finally, construct validity is the extent to which scores of a tool are correlated with a construct that we wish to measure. And a construct can be thought of as an idea or a concept. My doctoral project, I looked at NURS's self-efficacy. It was very important how I chose to define self-efficacy, and that I chose a tool that would define self-efficacy in the same way that I intended it to be defined. It should come as no surprise that the quality of the tool used to collect the data and how the data is measured have a direct influence on the strengths of the findings and the inferences that we are able to make from those findings. Internal validity is defined as the extent to which we can say with any certainty that the independent and dependent variables are related to each other. The strength of the internal validity of a study is often evaluated based on whether there were any uncontrolled confounding variables that may have influenced the potential relationship between the independent and dependent variables. Confounding variables can cause a change that actually makes our findings less accurate. So you want to consider, was there anything else going on within the study that may have impacted the study? One of the ways to reduce confounding variables is to use a random sampling design, which ensures all participants are equal in as many ways as possible, and that helps the study results. We also need to be aware of the Hawthorne effect, or the idea that people change their behaviors when they know they are being studied. This is a common confounding variable that can impact internal validity. External validity looks at whether the results of the study can be generalized beyond the study itself. Are we able to use these study results to make inferences about the population? And so we want to really be careful because our external validity is also influenced by the characteristics of our sampling, which goes back to the importance of sampling. Reliability and validity are both important concepts to consider when you use a measurement tool. It is also important to note that reliability always comes before validity. An instrument can be reliable, it can be consistent, but that doesn't mean that it is valid. That doesn't mean it is hitting the point, measuring what we want it to measure. However, an instrument cannot be valid. It cannot measure what we want it to measure unless it is first reliable. And I encourage you to pause and think about that very important concept for a minute. I hope at this point you have started to make the connection between these foundational concepts of statistics and how they guide and direct evidence-based practice. When we are looking at performing an evidence-based practice or research project, one of the first things we have to consider is the data that we want to collect. What data do we want to collect? That is going to help determine our sample. And based on the data that we want to collect, that will help us figure out if we can collect data on a random sample or if we must use non-random sampling to collect our data. We also want to consider our variables when we are collecting our data. We want to consider what are our quantitative variables. Are they discrete? Are they continuous? What are our independent variables? What are our dependent variables? What are the levels of measurement of our variables? And how is that going to impact how we can analyze our data? We also want to consider the reliability and the validity of the tools that we choose to use. Are we using a tool that is going to give us consistent results? Has the tool been determined to be reliable? And if so, is the tool valid? Is the tool measuring exactly what we want it to measure? And all of this comes together to ensure that our hard work is going to produce results that can be generalizable and applicable to practice change.